Welcome to today's June 21st Springboard Data Science Office Hour, the summer solstice for those in the Northern Hemisphere. But welcome to all of you today. We're really excited. We have a Capstone project. Before we jump into that project, we have a co-host. We have a new co-host to this session who will be joining us every week to even further the insight we're providing to your questions. So I'm excited to introduce him and have him say something about himself, but that is Mohammed Zakaria. Zakaria,
yes, very good.
Yeah, but welcome, Mohammed.
Hey, everybody. I'm very excited to be here. I've been looking forward to participate in these exciting sessions, and hopefully I'll have some useful feedback and comments about your presentations or some thoughts we can share. And I'm looking forward to learn from each and every one of you.
Cool. So next week we're going to pick his brain a little more, but today we have a Capstone project. Before that, I'll introduce our other co-host. So Mohammed will be working with AJ Sanchez.
Hello, everybody, and welcome again to another session of Office Hours. We are very excited to have Mohammed, our new co-host, and also Taesun Yoo, who's going to give us a presentation on his Capstone project. And as usual, we have a pretty energetic crowd, and we're looking forward to hearing your questions and listening to Taesun replies to those.
Cool. Well, let's jump right in. If any questions come up while Tyson is presenting, feel free to throw them in the chat box or hold them to the end. We'll definitely open up time for those questions. But with that, introducing a graduate from our intermediate data science Python course, here to present his project, Taesun Yoo.
Okay. So I'll be taking one. Hi, everyone. So my name is Taesun. So I'll be presenting about my Capstone project. So let me just share my screen. Can everyone see it?
Yes.
Okay, so let me get started. Okay, so today's Capstone project is focusing on talking about cardiac stroke risk stratification using a classification model. Okay, so here is brief agenda on what I'll be talking about today. And let's get started with some of the background. So before I begin, let me start with some of the background statistics. So cardiac stroke statistic within the United States in 2017. So 1 in 20 deaths actually account for the cardiac stroke events. And among all cause of deaths in the United States, it actually ranks number 5. And about 795,000 people experience a new or recurrent stroke events. And finally, the estimated indirect and the direct cost per stroke treatment is about 52 billion US dollars. So why should we care about this problem? There are three things that I want to highlight. It is that stroke is actually a preventative condition. So what that means is basically with your proper management of dietary and eating behavior, like with exercises, you can actually improve your outcome, like condition. So also the second thing is there has been an increase in our projected percent of people having more stroke. And the third thing is increase in cost for the stroke treatment. So our potential stakeholder will be cardiac care intensive unit managers and a group of clinicians. So the goal of this project is to predict patients with high risk of developing a stroke. And there are two main objectives: help physicians to take proactive health monitoring. Second, target prevention on these patients with high risk of developing a stroke. So here is a dataset overview. So this dataset actually comes with the 11 input feature for predicting one output stroke label. There are about 8 categorical and 3 numerical features, which contains information about lifestyle, health, demographic indicators. And then the sample size of this dataset actually comes about 43,000 observations overall. And here is a snapshot of the dataset. If you can look at it, there are 11 features and a 1 class label. So this dataset comes with 3 major challenges. First, this dataset was highly class imbalanced. So what that meaning was about 98% of the observations were non-stroke, like healthy cases, and only 2% of the observations are the stroke cases. And the second thing is there are some obviously outliers and duplicates. And third, some missing values on certain features. So before we build any type of machine learning model, we need to perform a data wrangling. So data wrangling, in my definition, is focusing on data cleaning and data transformation. So first, let me highlight this into five major steps. So first, we load the raw data into the Python as a data frame. And the second, we need to treat missing value replacement. Depends on the situation. There are two main methods to deal with. So for example, if your feature is missing more than 50% of observation in a certain feature, you might drop that feature because it's not going to be useful, even if you impute them. And the second thing is with the feature imputation, usually we replace them by a measure of central tendency, such as mean, median, and mode. Depends on the type of variable we have, as numerical or categorical, like ordinal, etc. And third thing is basically, after we did this, we need to handle outliers. So there are many ways to handle outlier, but I chose to use this method, interquartile range, which is a very traditional in the statistic. So as you can see on the right figure, the right sub-figure, it's a box whisker plot. So box whisker plot is basically a graphical representational tool which highlight 5 major stats: mean, maximum, median, your first quartile, and the third quartile, being 25th and the 75th percentile. So using this interquartile range, I can compute the lower bound and upper bound threshold. So basically what happened is if a feature in your if a feature in my value is actually sitting below or above this threshold, they will be treated as an outlier, and then we will just simply remove them from the entire observation, the data set. Then first, we need to execute the resampling. Resampling is very important because, as I mentioned earlier, in my data set, it was highly class imbalanced. So in order to deal with this problem, what I actually did was I took the downsampling approach, basically taking a negative subsampling from the major level, being non-stroke cases. So what I ended up doing was matching the sample size of the stroke cases with the random selection of the non-stroke cases to have a 50-50 like equal proportion. Well, we could have tested different proportion, but in my cases, I ended up doing equal proportion. And then we apply a feature transformation. So feature transformation, in my definition, is divided into 3 subcategories. So first, feature encoding, basically converting your categorical features into the numerical format that can be understood by your machine learning algorithm. Second, feature engineering. So using an existing feature, I'm going to generate a new feature. And then the last thing is feature scaling. So feature scaling is basically we're applying a feature scalar function. There are many types of them, but in my case, I actually use a min-max scalar function. Basically put the different features of a range into a similar range of scale, because some classification algorithms are basically sensitive to distance. So in order to minimize this impact, we need to handle this properly with the feature scaling. So here is a machine learning model workflow, overview of my model workflow. So it's actually divided into 2 stages. So stage 1 is focused on model training and tuning. And stage 2 is focused on the final model performance estimate. So basically in a stage 1, I load the raw data into the Python, perform data wrangling step, as I mentioned earlier, and then execute the data partition. So when we're executing the data partition, basically what I'm doing is I'm taking the original training set and then divide it into training set, validation set, test set into this ratio that I defined, let's say 50%, 20%, 30%, etc. So using a training set that I exploited earlier, I'm just going to build my model, train my model. And then once model gets trained, I'm going to use my validation set to further validate my model for like hyperparameter model parameter tuning to further optimize to get the best model performance. And then once I completely train my model and validate it, I'm going to use my holdout test set to actually test my evaluate my model performance across the different classification model that I chose to test with. So now, before I begin, let me highlight a little bit about the exploratory data analysis that I did. So as you can see on this slide, so this is basically showing the distribution and a histogram for the in terms of age, body mass index, and average glucose level for 2 different populations, being a non-stroke and a stroke cases. So the major take-home message here is that in terms of age, most of the stroke patients are senior, as you can see on the histogram with the orange coloration, because the histogram is very skewed to the left. And then in terms of body mass index, it was quite interesting, as expected, showing a normal distribution pattern. But then the body mass index range actually centralized from 25 to 30, in my point of view. And then the last thing is, in terms of average glucose level, it actually showed a non-normal distribution especially on the stroke patient population with the orange label, you can see that it looks like some kind of like a bimodal peak, like a bimodal hump in the lower and the upper range of the average glucose level. So now, in terms of lifestyle factor, what I ended up doing is I plotted a bar chart for 2 different populations using different calorical variable that I chose. So in terms of occupation ratio, it was quite interesting that most of stroke patients and also non-stroke patient seems to be working in a private or self-employee sector. And then in terms of marital status ratio, most of stroke patients are actually married compared to being a single status, which was, I thought, quite interesting. Maybe it could be a selection bias. Sampling bias, but who knows. And in terms of gender ratio, you can see that this was quite interesting too, that for both stroke and non-stroke population, there are actually more female patients than a male patient for some reason. And then in terms of urbanization ratio, so what that meant is, so people actually reside in the urban area or the rural area, there are no difference for two population. So finally, in terms of health indicator, I ended up plotting the 6 pie chart for the 1 stroke group and the non-stroke patient group. So so the take-home message here is that in terms of smoking status, it seems that actually there are more proportion of people in a stroke patient population are actually smokers than the non-smokers. And then also with the hypertension ratio, there are more population in stroke patient like had a higher the proportion of people being actually have some history of hypertension. And also with heart disease, it actually holds the same truth, that being that there are more high proportion of stroke patient population who actually have some history of heart disease compared to a non-stroke patient population. And this is just a correlation matrix plot of the balanced data set after I did the resampling. So as you can see here, the take-home message here is that on a correlation matrix plot, the most significant predictor that I had was actually age with a correlation value of 0.59, which indicates strong positive correlation. And there's some positive correlation, like very weak positive correlation with body mass index against stroke and average glucose level. So now let me talk about the model selection and the result. In terms of model selection, I actually ended up testing 4 different models. And then actually my 5th model is a 1 combined model, which I'm going to talk soon. So for the first model is a logistic regression, as everyone knows, is basically using a sigmoid logic function. Then I'm actually transforming the input value of feature into the calculated into a probabilistic range into from 0 to 1, saying that, let's say, if it is less than 0.5, then those cases were classified as non-stroke cases, if the probability is greater than 0.5, then those cases are a stroke. It works well on a linearly separable classes. And then for the decision tree, the second model was a decision tree. Basically, what it does is it split the data on the feature that I selected, and then it repeats this splitting procedure, and then it continues to split until each tree node left with the same class level, meaning that every sample has either cases with or the sample with only non-stroke cases or the stroke cases, basically. And the random forest is type of an ensemble learning model. Basically, it creates many decision tree, and it averages the performance of the tree prediction. And then the fourth one is the gradient boosting model. So it's kind of a type of a sequential training model in a stepwise forward fashion. So what it does is it learns a mistake from a previous model, and then it keeps iterating and then minimize the mistake, the residual error of it, and try to improve the accuracy of the model. So my first final model is a majority broad classifier, according to some machine learning textbook. So basically what it is a meta classifier. So what I did was actually I combined all the 4 models and then basically improve the accuracy of model performance by taking a majority vote, a majority prediction made for each observation. And this is just a feature importance plot. So in terms of feature selection, there's a couple of classification algorithms actually support this feature importance module, which are decision tree random forest and the XGBoost, which is a type of gradient boosting. And here I'm showing an XGBoost model for feature importance plot because that actually performed the best in terms of the model accuracy. But anyway, so the take-home message here is that there are top 3 selected feature based on the XGBoost model was body mass index, average glucose level, and the age. So now for moving on to the model comparison. So here is basically a summary table chart showing my model performance in terms of the accuracy, precision, recall, and ROC score. So overall, in terms of the evaluation metric, the best performing model that I had was a majority bold classifier with the accuracy of 80% and ROC score being 80%. So now moving on to confusion matrix. So this is a confusion matrix table, the result I obtained from a majority bold classifier. So basically the take-home message here is that the confusion matrix is a tool to tell you that like how many of the predictions are made correct and how many predictions are actually wrong. So overall, I was able to get 80% of correct predictions on both non-stroke and stroke cases combined. But then there are 20% of misclassification errors are made. So the take-home message here is that the balance between a machine learning model and a human intervention is required, especially on the 9% error, which is a type 2 error called false negative. The reason I'm saying here is that because these are false negative cases, is basically the cases that model actually thought or interpreted as non-stroke. But these cases are actually indeed was a stroke cases, which is really bad in the medical field or any type of medicine, because if you ended up missing these patients, it actually leads to the complication in a worst case scenario that actually reduce the mortality rate of the patient. So here is the ROC curve and the Precision-Recall curve, which is showing a similar type of information in a little bit different way per se. So for example, on the left-hand side of the figure, it's a ROC curve of the 5 model that I plotted. And as you can see, the majority bold model, the area under the curve is indicating the 0.86. So meaning that basically, in my definition, is that about 86% of time, this model is worse to test it than random guessing, which is 50%, to actually separate the stroke cases from non-stroke cases. And on the right-hand side, you can see the Precision-Recall curve with the weighted average mean of about 82%, indicating that about 82% of the time, my model is actually good at making stroke predictions from a total number of actually stroke cases. So here is just a summary recap of my project. So in terms of goal, model was able to predict the cases at high risk of developing a stroke by classification model. And then result was the model was able to predict whether or not the patient were at risk of stroke. 80% of accurate predictions are made on the test set. And in terms of risk and mitigation, when model incorrectly classified with 9% of error as likely patients are non-stroke cases, but in fact they had a stroke. So the mitigation strategy here that I'm emphasizing is that we need to review these identified cases with the group of subject matter expert being a group of clinicians, people making any clinical decision making. So the next step will be a collection of more meaningful features and a model improvement, which I'm going to talk about more in detail soon. So in terms of future works and recommendation, so the limitation is that basically what I think is that I have some absence of the useful feature or attribute. So basically what I'm trying to say here is that instead of having a categorical variable, like, having a bimodal, like hypertension, having hypertension, yes or no, or the cardiac stroke, heart disease history, or the hypertension, hypertension. I would rather actually wanted to have a the blood pressure measurement and genetic predisposition, physical activity level, things like that. And also I noticed something like a weak feature interaction among the categorical variable, especially that I mentioned earlier, like, the smoking status and the hypertension. Yeah. And in terms of the future work, this is actually follows along the same point that I mentioned earlier, which is collection of more meaningful feature, like genetic predisposition and physical activity. Especially I want to mention the genetic predisposition because when I was analyzing the data set, some portion of my stroke patient population are actually a younger patient, like, let's say like age, like teenager age or something like that. So sort of this type of variability cannot be explained with the feature set that I have in my data set. So I definitely want to have some like genetic predisposition, some kind of other factors. And in terms of model improvement, I could use a different approach, having a stacking approach or other ensemble type of learning, which is like other boosting tree and things like that. And in terms of this resampling strategy, there are other types of resampling strategy, like smooth synthetic sampling approach. And instead of downsampling, I could have done an oversampling on a binary class. So, because in my case, actually, I performed the downsampling, which actually worked well. And finally, in terms of the model design, instead of building a one model, I could actually build a two model, like in an age stratified classifier. So what I'm trying to say is that have a one model for a younger patient cohort, like let's say age less than 30, and then another model for like senior patient cohort for like older than age 50, for example. So based on my model and the analysis, so here are my recommendation is that I want to actually recommend my potential client being that we need to add additional stroke screening tests at a recommended age before 65. The reason I'm saying 65 because the mean stroke patient population, the age of mean stroke population are around 65. That's the only reason. And the second recommendation is questionable, more meaningful feature, because with the only feature that I had, it was not really enough to explain other types of the feature interaction or the variability in terms of correlation with the stroke, like my output label. So I definitely want to recommend the hospital to collect stress level, physical activity, blood pressure, and other type of genetic factors. And third, my last recommendation is conduct cohort study with the feature engineering technique. So basically, it's just like stratifying the patient cohort into more, let's say, a diabetic or obese patient group. Because in this given data set, which actually we can do that because I had a body mass index and the average glucose level. So using this, I could actually classify, like stratify them into different categories, like non-diabetic, diabetic, and obese patient group or non-obese patient group, things like that. So thank you for listening to my presentation. I really hope you guys enjoyed it, and then I look forward to hear more, thoughtful, insightful questions. Thank you.
Awesome, Taesun. Well, that was the perfect 20-minute frame we were shooting for. If you want to unshare your screen, we'll open it up. Anybody has a question they want to kick it off with? We would love to get those going.
The first few things I would say, like, really wonderful presentation, but I would add that stakeholders for this are limitless. You're just limiting yourself by mentioning only one person, one identity. Insurance companies would love to know about this. The veterans, the VA would love to know about this because they manage their own healthcare and their own health benefits. Probably every employer will be interested in that because they can get a discount if they can target this and be billed on generally on a lower rate for insurance. Mm-hmm. So, like, this is a very useful this is a great project for a very, very widespread problem. The other thing I would like to mention, what is the source of the data that you got it from?
The source of data was actually, I didn't put it up here, but in my project, the Capstone code in a GitHub, it was actually the data set that I actually retrieved from the data science competition. One of the data science competition is called from website like Analytic Vidya. Yeah, I think it's like an Indian hosted like the data science competition, kind of like a type of Kaggle. But this data set, it was actually an anonymized real patient data set that was actually submitted to, based on the description of data. I think it was one of the consulting companies in the US, I think McKinsey. So they were they were hosting this competition. Basically, they had an anonymized patient of the data set with this 11 features, and they want to actually the participant to build a model, the stroke classification model with the highest like AUC score or whatever. But yeah, in my case, I took this data set, did more exploratory data analysis, and
no, this is fantastic. Like, two things: would you be able to get something like the zip code, or if the dwelling is like urban versus suburban, like the kind of a lifestyle, like if somebody is living in New York City versus somebody is living in the countryside, that might be. Yeah,
that would be more helpful as you mentioned it, because actually, let me actually, let me just quickly show my screen on this.
I don't want to hug the discussion. I will just say one last thing. It would be regarding the BMI index. Probably you should bin that into different 3 or 4 bins, because BMI of 30 is not much different than BMI of 29.
Mm-hmm.
This goes throughout the stratification of the cohort you're looking towards. So that's also a good thing to do. But all in all, wonderful presentation and really nice models. Excellent tool to train up. And I noticed that for the most part, they're quite comparable in their accuracy. So that was indicative. And congratulations! I'm very happy. This is the first project I saw here.
Thank you very much. Yeah,
that's the bar too high.
Yeah, I took a lot of effort in it, but thanks for your advices, because those stakeholders that you mentioned, I never really thought about it, because although the data set was actually a US data set, right? I mean US patient data set, but actually I listed in Canada. So the healthcare policy, it works a little bit differently. So the insurance company doesn't play that important role as in the US. So as you mentioned it earlier, yeah, those are some really insightful thoughts that I never really thought about. Yeah, so thank you for mentioning that, and also for other comments. Yep.
Really great. Did you want to note something on the screen, Taesun, or you want to unshare it?
Oh yeah, sorry. Yeah, no, I was just showing it because just the data set. I mean the overview of data set that I just want to highlight. But yeah.
Yeah, that's great. Some questions in the chat box. Let me see.
Oh, okay. Yeah, let me.
I can ask these. So let me see. Yash asked a question. He said, "Hello, sir. He would be interested to know how were the parameters tuned for the 2 tree models." Oh,
okay. Okay, so you mean I guess he mean probably decision tree and a random forest. So basically what I use is that in a Python, there are actually I would say 2 ways to do this. So you could use a Greasearch CB, but in my case, actually I use a randomized search CB. Well, actually first I use Greasearch CB. Then my mentor actually recommended to use a randomized search CB. It works a little bit in the same way. Like, I mean, the reason I'm saying that is because you can actually define your parameter range and things like that. But randomized search CB is definitely much better in a sense that you could actually randomize it to get the best model parameter. So for example, let's say if I, for the decision tree cases or the random forest, actually for the random forest, right? Because the number of estimator is also important parameter, and there are like other parameters those are important. So if you use a randomized search CB, or you can first test with the Greasearch CB, then I'll actually recommend you to use a randomized search CB, just to have a better understanding of what are the different options you could use it to further tune and like get the best optimization of your model of the hyperparameter. Yeah. So does that answer the question? I guess.
Yeah. Some great questions. This is awesome. Another student asked, "What's the bottom line of accuracy? The data is quite unbalanced." I don't know.
Bottom line of accuracy. I'm not so sure what does it mean by bottom line of accuracy. So you mean like you mean probably before I did the resampling?
I'm not sure. If the student wants to elaborate, you're welcome to.
Yeah.
Unmute yourself or also comment. But
yeah, you can comment on chat box. Yeah.
Yeah, we could go back. Another question from Castor: "Why did you think of using logistic regression, random forest, GBoost over other algorithms?" So why did you choose the algorithms that you did?
Oh, actually, I tested most of the classification algorithm of all of it, but I just choose first I started with logistic regression, because logistic regression, actually I mentioned in my slide earlier that it works really well, especially linear separable classes. But in my problem, actually, is that let's say if I plot stroke and what was it, age in like a scatter plot, right? You could see that actually I didn't have it in my presentation slide, but you could see that it's perfectly linear. So what I mean by that is, let's say there are like a lot of cases are 1, like it's sitting on like over here, and then a lot of cases are like non-stroke, which is 0. So the logistic regression is, although it's a simple model, it works really well on the linearly separable classes. So my recommendation, the reason I did that is because always it's best to try with a simple model and see how it works, right? And then if it doesn't really work, then we do like data wrangling or further tuning and things like that, and then scale up. Try to use a little bit more complex model I'll say. So that was the only reason I chose, okay, logistic regression, start with first that model. And then, okay, it worked okay, like, but not the best. So can I further tune with other model, like decision tree and things like that? So that was the only reason, like a logic behind why I tested like logistic regression first, decision tree, random forest. And then, yeah, from decision tree to random forest, because usually ensemble learning performs better because I don't know the super detail about the algorithm logic, but it works in a way that basically, for example, even for random forest, is because it creates like many decision tree, right? So basically, it's type of like a majority voting type of, in a nutshell, it's type of majority voting. So let's say what I'm trying to say is, if you have a 5 candidate, right, and they're voting for some whatever decision you made, and then let's say majority of people actually voted as a 4 versus 1, then that's more accurate, right? So it's type of that kind of analogy. It's not really accurate, but that's kind of my simple analogy to explain it why I use ensemble learning. So that's a kind of like logic shifting from simple model to ensemble learning model and things like that. Yeah.
Well, I'm on mute. A few other questions. I want to get those asked, but I wanted to see if AJ had any feedback or possibly any question, and then we'll get to those questions.
Well, Taesun, I'm really impressed by your project. I think it was very comprehensive. You almost crossed all the I's and crossed all the T's and dotted all the I's. One question though, to show you my appreciation, is that when you apply undersampling or the way you call it downsampling, there's an interesting combinatorial opportunity there, because there are multiple subsets of the size of the minority class that you can take. So both combinatorially and statistically, it presents itself as an interesting proposition, right? Did you and or your mentor thought about exploiting that?
Yeah, we did. But I mean, because the resampling is, I mean, for any class imbalance problem, regardless of being a different use cases, it's the most significant problem, right? So, I mean, there were a lot of options I had, but the reason I start with actually downsampling was that because we had a lot of non-stroke cases, like 98% of them from the 43,000 observation, right? So that's why I chose downsampling. Then, as you mentioned, the selection method, right? Actually, what I did was I think I used one of the module in the Python that actually randomized and then select the subsample of the non-stroke cases. I mean, my majority class level. So that's what I took as.
But you took one sample from the majority class, though, right? Even though it's a random sample, you took one sample.
Yeah. Because the reason I did that was, one sample. Because the reason I did that was I just try to match with the sample size of the stroke cases. So what I defined is, with the randomization of one sample, I was sampling the same sample size as the stroke cases, because I believe the stroke cases that I had, about the 2% of the whole data set, I think it was around like 1,500, I think. So I took the same sample size of 1,500 from one sample of through the randomization. But actually, I tested that, but I don't think I highlighted in here. But what I actually did, the most important thing I did was I actually binning the ages, because the reason I did that was the age was very what am I trying to say? Most significant predictor that I had in the data set. So I knew that definitely there's some for example, usually more senior patient will have more stroke cases for whatever reason. So that's why, so my mentor recommended me to, you know what, let's take a age group discretization approach to actually use the feature engineering to further group them into like different age groups. So what I didn't actually show it on here, but what I actually did was I break down my samples of the non-stroke cases into different age group. Let's say from less than 30, and then 30 to 40, 40 to 50, 50 to 60, 70 to 80, things like that. And then actually, when I did that, and then what I did was I wanted to try to match the sample size of the. I want to match the exact sample size as the stroke cases, right? So what I did was for each group, with the proportion that I get for the different age group, I took the samples from different age group, and then just the total size of the sample from non-stroke cases were actually the same sample size, which is 1500. Yeah. So the entire the sample size that I had was around 3,000. Yeah.
Very good.
Yeah, that was
congratulations.
Yeah, thank you.
Good question, AJ. Daniel had a great question, and then I wanted to ask him, and I think it goes down the same alley. But curious for you, Taesun, how long did this project take you from getting the data, finalizing this idea, to being here today? How long did this take you, and maybe how much time did you really put into this?
I think that's a good question to ask. I think I put really a lot of hours than the recommended hours in the Capstone. What do I call it? The Capstone guideline, or the curriculum. Because in the Capstone curriculum, I mean, because this Capstone is breaking down into you have to submit your milestone, and then some data wrangling, and the exploratory data analysis, and then the final project. So overall, if I combine everything, I would say 50 to 60 hours. I think I put a lot of effort into this. The reason is actually because, well, I mean, the reason is the first initial stage, it takes a bit of time because you need to choose a data set that you want to work with, right? And then there are a lot of different models that you could use. I don't know, you could use you could build regression model, try to predict some housing price in San Francisco, for example, or even my classification type of case, or things like that. So I think the first thing is it depends on how you actually narrow it down of what you want, basically choosing your area of interest, different industry, and then your model, or your approach. So yeah, but anyway, in a nutshell, I think overall, I think it took estimated hours 60 hours. Yeah.
Great question. And I have a follow-up for that I love asking all of our guests and any completed student. For anybody just starting out in the course or just starting out on their capstone project, what is maybe some advice you would give them to get through those blockers, to get through those challenges that might come up? Is there any advice that you found helpful that maybe you wish you would have known?
Yeah, I think the first that actually stays along with the first comment I made was choosing your data set earlier is really important. Because because in the initial, I think the mandatory assignment, there's a section says, what was it? Capstone idea, Capstone project idea, whatever. You have to submit that. So I proposed 3 ideas. So from one of my idea, I had some proprietary data set that I wanted to actually present it, but I actually discarded that idea because there are a lot of complications regarding confidentiality and things like that. You don't want to waste too much time on doing that data collection, getting the confidential agreement and things like that, right? So I think it's really important to choose a simple, but not too complex data set to work with, because the data collection, the data wrangling step is the most important step to get all the proper step done, doing the data exploratory analysis and the machine learning model. So I would definitely recommend that choosing your data set carefully earlier, and then discuss your option with the mentor frequently. I think that's the 2 most advice that I could actually give to other new students starting project. Yeah.
Awesome. Well, we've kept you and everybody along, but wanted to say thank you. I think an awesome presentation, and I spoke with Taesun at the beginning of the course, so it's awesome to see him come full circle and be presenting here. So wishing you the best of luck. Come join office hours anytime. We'd love to have you back. And then to all the students, I included my email. If you have any questions that didn't get answered, I will forward them to Taesun. And that's all. Mohammed, thanks for joining. AJ, as always, thank you. And then the students, thank you.
Yeah, thank you, everyone. Yeah, I really appreciate that. I think, once Chris actually sent me a question, or I think I can retrieve some of them. Actually, I can post it on our community web page, I think. Yeah.
Definitely. And I'll upload a recording of this so people can access that in the office hour channel. But that sounds good. Next week we're gonna pick Mohammed's brain a little bit. We didn't have enough time to do that, so come. We're gonna really. You better come prepared. We're gonna really. You may have been. Oh wait, you may have been muted. What was that, Mohammed? Oh, I'm losing you. You're muted. You gotta unmute.
Looking forward to it. Looking forward to it.
Perfect. All right. See y'all. Tyson,
Bye-bye.
awesome. Thank you, guys.
Thank you. Bye.